If I may, I have a question. So
Sure, please.
thanks a lot. It was brilliant. So I learned a lot of new stuff, and I'm not really a mathematician because of that. I want to ask a naive question from an engineering perspective. You had one of the examples, I think maybe two or so, where you had this nice honeycomb architectural material, and then you mentioned that if I try to choose M is equal E. So do you have something in mind how you would be able to choose M is equal E in this kind of material?
Yeah. Sure. Yeah, I do. I didn't explain this because I was running out of time. So what this represents for the honeycomb lattice is you have your dispersion relation. So you have your frequency as a function. So your frequency as a function of wave vector. Now it's at the corners of the Brion zone. So they're just particular choices of K. So like here, then the dispersion relation looks like, well, in general, it looks like this. So you have a gap between a band above and a band below. And this is just, you get this just from solving the equations, let's say using COMSOL or something. E here would represent the frequency. So when I change E, I'm moving up here. The M you choose in the honeycomb lattice, the M you choose by making, so a unit cell like is shown here, this is a unit cell of the honeycomb lattice, by making these two different. So you've got two scatterers in your unit cell. If those two scatterers are completely identical, then this band gap closes and it just becomes like two cones joined together. In that case, that would be M is 0. But then by making these two scatterers different, depending which one you make different, would choose the sign of M. And then you open up this gap. So that's how you would tailor the values of M and E in the honeycomb lattice.
Okay, thank you. Excellent. Thanks a lot.
Very quick question. Are these accidental and not symmetry induced Dirac cones you use or you have before the band gap?
In the honeycomb lattice, it's a symmetry. Oh, do you mean in general, or?
Yeah, in your example.
So in this example here, it's symmetry induced. So this would be in the honeycomb lattice. So you get it from the C3 symmetry at the K points. So that threefold rotation symmetry. But then by breaking that, by making these two scatterers different, you break that symmetry and open up the gap.
Yeah, would be interesting if you can say a couple of words about the difference between the honeycomb lattice and square lattice, for example, using.
Okay, yeah. You mean like because the square lattice, you mean in terms of this theory here?
Yeah.
So long as you can still cast it in the same language, though. I think even for the square lattice, you can still write it. You must be able to still write it as an effective Dirac equation because the only thing it relies on is there's two bands. So long as you can make the approximation that only two bands matter, then you're going to get some equation that looks like this. So it may in general you'll have other things in here. So it's not going to be as nice as this. They might have some constant here and some other constant here sat next to the two derivatives. But still, when you go to M is E, then provided it takes this form, then you're still going to get some sort of equation that indicates that the wave can only circulate one way. So this kind of equation that I got from crystal optics that, well, this is the Cauchy-Riemann conditions, Cauchy-Riemann conditions. So I think the square lattice, well, need a bit of thought. It might be interesting. But I don't think there's anything that would fundamentally stop it.
I mean, is there any difference between using square lattice and hexagon in order to transport energy around the sharp bands, or?
Well, you don't have the same nice symmetry, do you? At the K points, so not. I'm not sure how well it would work for the square lattice. I think, yeah, I'm not sure. I'd need to work it out for the square lattice.
Okay.
I don't see any reason why you can't use the same ideas.
Yeah, I was just I was curious about the difference it made using
well,
squares.
I can sure tell you that in deriving this equation for two bands, starting from the beginning, then the C3 symmetry at the K point, at these points in the Brion zone is really important to get an equation of this form.
Yeah.
But okay, maybe with some assumptions, then the square lattice can give you also something that looks like this.
Okay. Any other questions? Yeah, Mohammed? Please just unmute yourself.
Hello.
Okay, thanks.
Hi, thank you. Thanks for this nice talk. Yeah, I have a question regarding this complex direction. So, does this correspond to the material or to the wave, like having inhomogeneous waves?
So if we go back to the, I think it corresponds to the derivative of the wave being 0 in a complex direction. So it's the material makes for these particular kinds of materials, the material induces this derivative to be 0. Just like in a normal 0 index material, it just makes the wave spread out to being uniform everywhere. In these materials, then it makes the wave obey the Cauchy-Riemann conditions. It makes it obey this complex derivative being 0, which then makes it circulate just one way. Does that answer your question? I mean, there's no inhomogeneity in the material. If that is the question.
No, because I know in acoustic, for example, if you have like inhomogeneous wave, you could have like a spin. This paper, like by Franco Nori and
they
have shown this kind of.
Yes. Oh, I see what you mean. Yes, and that's what this is all about. Okay. Yeah. So in this case, even in free space, you can associate propagation out of the plane with being equivalent to being as one of these strange materials where the wave can only circulate in one direction. And the inhomogeneous waves you get here, this one-way kind of surface waves that you have here are directly analogous to this paper that you talk about in acoustics. Where they talk about the spin momentum locking, where you have the inhomogeneous wave and then you have this sort of, you can associate with a kind of circulating with a spin depending on your direction of propagation. So I think there's a connection, but only in this special case where you're sort of looking at free space as if it was a sort of material.
Okay, thank you.
Any other question? I see many people working in the field. Sure, we'll have some questions. So just another very trivial question about the concentration. I mean the amplitude of the energy, the most you have. I mean in the band gaps.
Mm-hmm.
It is. I mean the scattering field can you say something about the way it behaves in the band gap and at the edge of the band gap after the breaking the Dirac cone, opening the Dirac cone?
Yeah, sure. Do you mean like? Do you mean? I mean, do you mean in any case? So even like in this system here?
Yeah, exactly.
Yeah, sure. So right now, this is in this case, you know, even just an ordinary isotropic material with a refractive index n, you can think of it as having a kind of Dirac cone, as in if you just have an ordinary isotropic material and you plot out the dispersion as a function of the value of epsilon. So I'm setting these off diagonals to 0 in this case. Then you know that you have negative index materials, if you like, for negative values of lambda, and then you reduce the magnitude of lambda up and up and up and up until it goes to 0, and then it becomes a 0 index material, and then it becomes a positive index material. So for all values of lambda, all values of epsilon and mu, then you're allowed, you have propagation, right? So the wave can propagate. There are allowed values of k. The thing is, when you introduce this gyrotropy, this I alpha, so in practice that's like sticking the dielectric in a magnetic field, just a static magnetic field, then that opens up a gap. So in that case, you've broken time reversal symmetry by sticking the thing in a magnetic field, and now there is a gap. So there is a region where you choose values of the diagonal of the permittivity and the permeability, and you're not allowed to propagate. So your k, there are no real values of k. And in that case, if you stuck a source in the material, it just wouldn't propagate anywhere. But there is something that can happen at the edge. So if you stick two of these materials together, then there can be a wave stuck at the edge. And that's exactly what the Chern number predicts. That's exactly what this Chern number predicts. So if you have a material with gyrotropy and you make it change sign, then, and you're in this gap, so that's that region of parameter space where you're not allowed to propagate, then the wave can be stuck at the interface, which is exactly what's shown here.
Slightly different than to elasticity behavior.
So in elasticity, there is an analog though. So that's this thing here. If you choose your stiffness tensor to, obey this thing in the box, that when alpha, when the off, it's a funny elasticity stiffness tensor because it's got complex off diagonals, but some sort of rotating, something rotating in the system. If you choose your value of alpha bigger than lambda, then again you have a region of parameter space and elasticity where there's no allowed propagation, and it's exactly analogous to this EM case. And sure enough, the wave equation is exactly the same. So you can simulate what the elastic wave does in this material in exactly the same way. Is that what you mean? I mean,
okay. Yeah, it is clear for me. Do you have any other question? If someone else, if not, we can contact Simon via email, and your talk will be online, so available for any time for any other curiosity. Okay, thank you, Simon. It was great having you, and see you all next week. We'll have Davide Quadrelli from Politecnico di Milano. So see you all guys next week. Stay safe. Thanks. Bye-bye.
Nice to see you. Bye-bye.